Okay, let's get into this. Electric fields and electric charges, also electric forces. There's a lot of stuff here, but let's just start with the fundamental forces. If fundamental interactions, we say everything is made up of this. Fundamental interactions. Why do I have to write this out? Should I write this out? Actions. Okay, so we have gravity. This is an interaction between objects that have the property mass, which is most everything. Then we have the electromagnetic interaction, which I'm going to actually break into two pieces, the electric and the magnetic. And these are really just two parts of the same thing, but in this case, I think it might help to break them up. Magnetic. And then we have two other forces, the strong nuclear force and the weak force. And so this is an interaction between objects that have mass. The electric is, let's put that over here, mass. This is an interaction between objects that have electric charge. This is an interaction between moving charges. And let's not worry about those other two. So now we're down to these fundamental properties of nature, right? We're talking about the electric interaction, and we're talking about the fundamental properties of matter. If you take like a Lego block, this Lego block is made up of three things: the electron, the proton, the neutron. And we like to think about fundamental particles, and if you could break this up as much as possible, and it turns out that the electron is, as far as we know, a fundamental particle, and we use the symbol E for that. A proton actually is fairly fundamental, but you can break those down, and the same thing for the neutron. So these are not fundamental particles at this point. But in this class, we're not going to break protons apart. We're not going to break neutrons apart. So the electron is a fundamental particle and has a charge of E, and we'll say that's going to be negative 1.6 times 10 to the negative 19th coulombs. The proton has the same charge but positive 1.6 times 10 to the negative 19th coulombs. And then neutron is neutral. Okay. So if I look at this block, it probably has equal numbers of electrons and protons, such that the total charge on this is 0. And so, but it can still interact with things. There's a lot of weird stuff about charges, but I really want to focus on how we describe this electric interaction using the electric field. Let's think back for a second to gravity, okay? Because it helps. I think that's a useful analogy. Let's say I have the Earth, and I have a mass right here. Well, what's the gravitational force on that? We say it's this, mg, where g is the vector. I'll write it in my favorite notation like this. I ran out of room. Newtons per kilogram. Okay, so this says that g is the gravitational field on the surface of the Earth, and it has a 0x component, a y component of negative 9.8, and a 0z component, and it has units of newtons per kilogram. If I take a mass and put it in this gravitational field, I get a force. So we could say this, Fg equals m times g. So it eliminates that mass part. One of the masses, right? We still have the mass of the Earth is actually in that g right there. So G is the gravitational field, and that's why it's really useful in your first semester physics to call this in newtons per kilogram. Although a lot of times they don't. It has the same units as meters per second squared, but newtons per kilogram says that per kilogram of mass, this is the force, 9.8 newtons per kilogram, downward. It is a vector. What if I go to the Earth as a whole? There's my Earth. If I'm over here, how would I calculate the gravitational force? Well, I would need this vector r, right, from the center of the Earth to that object, whatever it is. It's just we could call this a test mass. It has a mass just m, and this has a mass me for the mass of the Earth. Then the gravitational force on that would be, I'm running out of room here. Let's put it right here. Is this too low? I'm going to call it big G, is negative G, mass of the Earth, the other mass, over that distance, vector distance, magnitude squared, times a unit vector r hat. And we're going to talk about unit vectors. I think it's important. But that's just a vector in the direction of r that has a magnitude of 1. Now, I can actually write this as mg. So g is not 9.8 in this case. G is the vector negative g, mass of the Earth, r squared, r hat. Right? So all I do is factor out that m, and I get this other gravitational field g. And that's the gravitational field. And we've already done with that. And I think it's easy to think about the gravitational field because it's something that is kind of more in our minds. We deal with gravity all the time on the surface of the Earth. We actually deal with electric interaction more than you would think, but it's there too. Okay, so now let's go and look at an electric charge. Suppose here I have a charge. Let's just put it right here. I'm using this. That's my positive charge. It's a Lego piece. You like that? Well, I like it. And now I take another charge. So this is a positive charge. And this is another charge. This is a negative charge. Yellow. Again, I can create this vector r from one to the other. And so the symbol we use for charge is Q. So let's say this is Q equals plus 1, Q1, Q2 equals minus 1 coulombs. Well, it turns out that there's going to be an attractive force between these two, pulling them together. And we can calculate that force with Coulomb's law. So let me go ahead and write down the expression for Coulomb's law. This says that F, I'll call it Fc, is going to be equal to 1 over 4 pi epsilon naught Q1, Q2 over the magnitude of r squared r hat. So again, we have to find that unit vector r hat in order to make this thing work. And you notice it looks a lot like the gravitational force, except that I have this constant over here where 1 over 4 pi epsilon naught is 9 times 10 to the 9th newtons meter squared per coulomb squared. A lot of times people just write that as K, and I'm cool with that, whichever way you do it. Okay. But there's no minus sign here. And there's no minus sign because if this is a positive charge and that's a negative charge, this is going to be minus, right? This is going to be pulling in the opposite direction. And that's the nice thing about electric charges is that they can be repulsive or attractive, right? Where gravity is always attractive. But it does look a lot like that, but we have to have that r hat in here. This equation is called Coulomb's law, and it's empirically determined. Okay? It's experimentally determined that there's a 1 over r squared relationship between the forces between these two. And yes, if this exerts a force on the negative charge exerts a force on the positive charge pulling that way. Newton's third law still holds true. But what if I want to take this and divide by the value of that charge and factor that out? So I'm going to take this and divide by Q2. Then we get what we call the electric field. I can say E equals Fc over Q2, and that would be 1 over 4 pi epsilon naught Q1 over the magnitude of r squared, that's a vector, r hat. And this allows us to kind of get a picture of the region of influence due to this positive charge by saying, well, what is the force on this? And then I'm just going to take away the force. And then I can put it over there and measure the force and then take away the force. And I still get the force per unit charge, just like the gravitational field is the force per unit mass. Okay, so this is it. That's it. This is Coulomb's law. and this is the electric field. And that's it for this whole chapter, essentially. Okay. Let's talk about this r hat thing now. So let's talk about vectors really briefly. And this is something that a lot of algebra-based textbooks don't include. So they may say the electric field looks like this. They'll say E equals, I'm going to write it exactly how it is in a lot of these books. K Q1 Q2 over R squared. No, I'm sorry. That's the force. E equals K Q1 over R squared. They're going to write it like that. And that's the magnitude of the electric field, and that's the magnitude of the distance from the charge, and that's the magnitude of the charge. Now, the problem, though, is that it doesn't tell us anything about the direction. The direction is left up to you. And that's fine. Except what if I have a case like this? So there's another important thing called superposition. This says that the electric field due to two charges is the vector sum of the electric field due to individual charges. If I have this, Q1, and down here I have a negative charge, Q2, and I want to find the electric field right here, well, I can find the electric field due to Q1. It would be like this, pointing away because it's a positive charge, E1. And then the electric field due to that one is this way, E2. And then the total would be the sum of these two, so it would be something like this, E. And that's cool and all, but now if I have these these electric fields as just a scalar magnitude, then it's really difficult to add these as vectors because they are indeed vectors. So that's why I think it's useful to talk about the unit vector r hat. Let's go ahead and do the r hat vector. Okay. So let's say that I have a problem. So here is my charge. And here is where I want to find, I'll put it down here. There's where I want to find the electric field. So I have this vector r. So the unit vector r hat is defined as this. R hat equals the vector r divided by the magnitude of the vector r. And so that means that this has the same units as that, so this is a unitless vector. But this is what we call a unit vector because it tells a particular direction. You've already seen these, probably. Let's say I have a force that looks like this. F equals 3x hat plus 2y hat plus 1 z hat newtons. X hat, y hat, and z hat are unit vectors. They are unit vectors. X hat is a unit vector in the direction of x. Y hat is a unit vector in the direction of y. And in fact, if I wanted to write these as component notations, I could write x hat equals the vector 1, 0, 0. So it's 1 in the x direction, 0 in the y direction, 0 in the z direction. Y is the unit vector 0, 1, 0, and no units. And z hat is the vector 0, 0, 1. And so we use those. If I multiply 3 and then multiply this by 2 and then multiply this by 1 and I add these all together, I get f equals the vector 3 times 1, which is going to be 3, plus 0, 0, 2, 1. So I get it actually newtons. It actually works. Okay, that's important. So if I want to use this to find but see, here's the thing. Once I get electric fields, if I go back over here, and let's say I had E2 as a vector, I'm just going to make up some values, negative 2, 0, 0, and newtons per coulomb. And E1 is the vector 3, negative 1, 0. Now I have these in component notation. I can easily add them together. I could say the key to adding vectors is to add their components. So it's going to be negative 2 plus 3 is going to be 1. 0 plus negative 1 is negative 1. 0 plus 0 is 0. So that's why if I can get this in terms of unit vectors and write these as actual vectors, it's a way easier problem. If you just have these as magnitudes, you're stuck with a difficult geometry problem that's not easy to deal with. Okay, let's do a very simple case of the electric field due to 2-point charges. Let's do a couple cases. I'm going to do 2 examples, and then I think I will stop. And that this is a chapter where the ideas aren't so complicated. It's the practice that takes a lot. You have to do a lot of practice here. So let's say that I'm going to give some actual values. So I'm going to have a charge. This is the x-axis. This is the y-axis. And let's put a positive charge right here, plus Q1, and a negative charge right here, minus Q2. And let's give these values. So this is 0.01 meters. This distance, this whole distance right here is 0.03 meters. And I want to find the electric field right here at 0.05 meters. And now let's say Q1 is going to be equal to 5 nanocoulombs, which is 5 times 10 to the negative 9th coulombs. Q2 is going to be equal to negative 1 nanocoulomb. I'm just making this stuff up off the top of my head. I don't know if there's nothing special about it. And I want to find the electric field at this point right here, the total electric field. So I know that E is going to be equal to E1 plus E2. So I need the expression for E1 and E2 as a vector. And so this is pretty easy since they're all in one dimension. And then we'll do a problem that's in 2 dimensions. Okay, let's find E1 first. E1 is going to be equal to, I'll write it as K times Q1 over the magnitude of R1 squared times R1 hat. So what the heck is R1? R1 is this vector, right? It's the vector from my charge to my point of interest. So that's the vector R1. Can we get that vector by looking at it? I think that we can. Okay, because this is at 0.01, that's at 0.05. So what if I say the vector R1 is 0.0400 meters, right? Because from here to there is 4 centimeters or 0.04 meters. And it's not moving in the X, in the Y or Z direction, so those are both have 0 components. Now let's find the magnitude of that. That's pretty easy. R1 magnitude is going to be the square root of 0.04 squared plus 0 squared plus 0 squared. So I take the components, I square them, I add them together, and I take the square root. And so I get 0.04 meters. So I square it and I take the square root. Now I can find R1 hat. R1 hat is going to be equal to the vector R divided by the magnitude of R1. So it's going to be 0.0400 meters divided by 0.04 meters. So the units cancel, and this is a scalar division, which is the same as scalar multiplication. So I need to multiply each term in my vector by 1 over 0.04. So I get 0.04 over 0.04, and that's going to be equal to 1. 0 divided by 0.04, 0. 0 divided by 0.04, 0. And that's my unit vector, which we knew, right? We knew that was in the x direction, so we didn't really have to do that. It wasn't too difficult. Now let's do the same thing for, now we can go ahead and calculate the electric field E1. So E1 is going to be equal to K, I'll leave it as K, and then I'll put 5 times 10 to the negative 9th for the charge. I'm going to leave off the units there. Then I'm going to have R hat, which is 100, and then I'm going to divide that by the magnitude of R1, which is 0.04 squared, so it's going to be 0.04 squared. And let's get this in terms of K. I guess we can put the K in there too. So let's put this as 9 times 10 to the 9th. And let's go ahead and write this out and do this calculation. I'm going to use this calculator that I don't really like, and there's a better way to do this. We'll do it later, but I think people understand calculators better. And there's actually some great vector calculators that have vector notation in there too. So, But you do need to be careful with your scientific notation. So let's go ahead and do that. I'm going to say 9 scientific notation times 10 to the ninth times 5 scientific notation to the negative 9. So I'm going to put -9 times, let's leave that vector right there. How do you backspace? Okay, that right there. Divided by, I can put parentheses because I want to make sure I do it right. 0.04 squared, close parentheses, equals. So I need to multiply 28125, yeah, that's right, by the vector, by the component 1, and then 0 and 0. So I get 281, is that point? No. 2500 newtons per coulomb. Now, there's a trick here, obviously. Here I have a 10 to the ninth and a 10 to the negative ninth, right? So 10 to the ninth times 10 to the negative ninth is just 1. So you could just do 9 times 5 times and then divide by 0.04 squared. But I did it the long way. Okay, so that's E1. Now we need to find E2. For E2, the first thing I need is R2. Let me go ahead and write it here so we can see it. The vector R2 is from here to there. So that's 0.03 meters to 0.05 meters. So it's just going to be 0.0200. And remember, it had a -1 charge. So let's find E2. I'm going to write E1 up here at the top. E1 equals 2.8 times 1, 2.81 times 10 to the 4th, 0 newtons per coulomb. Okay, so R2 is going to be equal to 0.0200 meters. I need to find the magnitude of that. So the magnitude of R2 is going to be the square root of 0.02 squared plus 0 squared plus 0 squared equals 0.02 meters. Now I need to find R2 hat. R2 hat is going to be the vector R2 divided by the magnitude of R2. And so that's going to be, again, 100. Now I can find E2. E2 is going to be equal to K, 9 times 10 to the ninth, times times Q, which is -1 times 10 to the negative ninth. And then I need to multiply by that unit vector, 100, and divide by this 0.02 squared. So let's put that in our calculator. 9 times 10 to the ninth times -1 times 10 to the negative ninth is -9. So I have to take -9 divided by 0.02 squared. So I say, let's just put this as 9 divided by parentheses 0.02, which we could have done in our head, squared, close parentheses, equals. And I get the vector 2.25 negative times 10 to the 4th, 0 newtons per coulomb. So you'll notice that this one, because I had a negative charge, even though the unit vector was in the same direction, this electric field's in the negative direction. So I have, and also notice that they're close to being the same size, but this is actually a larger vector. So here I have E1 and then E2. So now I can add those two vectors. E equals E1 plus E2. And so that's going to be equal to 2.81 times 10 to the 4th, 0 plus -2.25 times 10 to the 4th, 0. I left off the units. So when I add vectors, I add their components. So I have 2.81 plus -2.25 times 10 to the 4th. I mean, we could actually do that in our head, but let's do it on the calculator. Put the calculator here so you can see it. So I'm just going to say 2.81 minus 2.25, and I get 0.56, but I still have that times 10 to the 4th. So it's going to be 5.6 times 10 to the 3rd, 0 newtons per coulomb. Okay, let's do the same charges, but I'm now going to I want to make it easy. Let's put 1 at the origin. I want to do, let's do the same charges. But now I want to find the electric field right here. No, I don't want to do that. I want to make it easy. Well, let's just find r hat for a non-simple case. And then I'll stop there, okay? Because this is, I don't want to do practice problems in a lecture. I want to do actual problems. So let's do, say I'm up here. I want to find the electric field up here, and this is a distance of 0.04 meters above that. So in that case, what's going to change? Well, I'm going to have to recalculate E1 and E2, and E1 is going to have an electric field unit vector in the y direction. But what about this one? Okay, that's the problem. What do we find for R2? So if I want to go from here to there, I'm going to have to go over 0.2 meters in the x direction and 0.02 meters, and then up 0.04 meters. So I can write the vector R2 as this. R2 is the vector negative 0.02, 0.040 meters. Now I need to find the magnitude of that. Let's do that. R2 magnitude. And this is a lot of tedious work, and that's why I'm going to make another video to show you how to do this in Python, because we can do a lot of, or a vector calculator. If you have a vector calculator, it's going to help out a lot. So this is going to be the square root of negative 0.02 squared plus 0.04 squared plus 0 squared. Let's go ahead and do that in our calculator. Clear. So I get 0.02. Clear. So I'm going to be the square root. I'm not a great calculator person. I hope you know that. Square root of, I don't need the negative sign, right? Because I'm squaring it. So I'm going to say 0.02 squared plus 0.04 squared. Close parentheses. And I get 0.045. Let's say 0.0447. And you'll notice that's longer. That's longer than either of those two, and that's the way it should be. Be very careful about your order of operations. If you're not sure if that needs to be parentheses around the 0.02, then put an extra parentheses in there, or do it one step at a time and write it down. You can get yourself into a lot of trouble with the calculator if you're not sure what you're doing. So just be careful. So now I can find the unit vector. R2 unit vector is going to be R2 divided by the magnitude of R2. So that's going to be negative 0.02, 0.040 meters divided by 0.047447 meters. So I'm dividing a vector by a scalar, so I have to divide each component by that amount. So I get R2 hat is going to be equal to, this first one is going to be 0.02 divided by 0.0447. So negative 0.447. It doesn't seem right. I guess it's just coincidence. Okay, so I get negative 0.0447. Now for the y component, I'm going to say 0.04 divided by 0.0447. And I get 0.895. And then 0 divided by that 0. And that's my unit vector. Now let's just double check. The magnitude of the unit vector should be 1. So let's just find the magnitude of R2 hat. That's going to be this squared plus that squared square rooted. So I'm going to get 0.447 squared plus 0.895 squared. And I did round, so I might get something a little bit off, but that's okay as long as it's close. So let's put that in. So I get square root 0.447 squared plus 0.895, is that right? Squared. Close parenthesis. And I get 1. Close enough to 1. Okay, so there I found a more complicated unit vector. And then when I calculate the electric field, I just multiply the kq1 over r squared times this, and I can get the whole electric field as a vector. Okay. I think what I'm going to do next, I'm going to stop here. My next video is going to be how to do this same kind of stuff in Python, because I think that really helps you see how these things work. So I'll stop there.